Hello everyone. We are studying decision trees. In the previous video, we studied how to build a decision tree using the Gini impurity and Gini index. In this video, we'll take a look at how a decision tree can be designed using the ID3 algorithm and using the concept of entropy and the concept of information gain. Given a particular outlook, temperature, humidity and wind condition, we can predict whether the person will go out to play tennis or not. Okay. So the first step in solving this problem is to find out the entropy of the entire data set. Now, entropy measures the impurity or the uncertainty of the data. Okay, entropy is nothing but the impurity or uncertainty of the data. Okay, so for example, in this data set, in the play tennis column, if I had all the rows labeled as yes, then there is no uncertainty or there is no impurity. Okay, so in that case, the entropy will be 0. Similarly, if the play tennis, the label column, had no on every row, in that case as well, the impurity or the uncertainty would be 0, because there is no uncertainty. The outcome is certain. If all the rows have yes as a label, the outcome is certain. Despite whatever, despite the weather, despite the temperature, despite the humidity, and despite the nature of the winds, the person always goes out to play tennis. So then there is nothing to decide over here. The answer is simple. If I have a question in my mind, whether the person will go out to play tennis or not, if all the rows are labeled yes in my data set, I can say with certainty that the person will go out to play tennis. And if all the rows are labeled as no, then I say that irrespective of whatever the weather, temperature, humidity and wind nature is, the person will not go out to play tennis. The person does not want to go out, the person will not go out to play tennis. So in that case also there is nothing to decide as such. Okay, so the entropy will be 0. So basically we call such data sets as pure data sets. So entropy is 0 when all the labels have a single value. All labels are same, then entropy is implies that entropy is 0. Okay, so when we will have maximum entropy, of course, as we increase the mix, as we have a mix of the labels, like here, if we measure, there are 9 rows of yes and 5 rows of no. 9 rows have been labeled as yes and 5 rows have been labeled as no. So in this case, there is a mix. The maximum entropy will be when maximum entropy. So maximum, you will get maximum entropy when exactly half the rows have different labels. What I mean by this is, in this case, for example, if 7 rows were labeled as yes and the other 7 rows were labeled as no, then you would have maximum entropy value. Okay, so how do we calculate the entropy? So this formula was created by Shannon, who is the father of the information theory. Okay, so we use the formula. So the entropy, let's call the entire data set as S, let's say. So this is my entire data set is S. So entropy of the entire data set S is given by minus probability of class plus or class yes multiplied by log of that probability minus probability of class no or class minus multiplied by log of that class. Log of the probability, basically probability multiplied by log of probability. Okay, and because probability is always a number which is between 0 and 1, the log values will be negative. Okay, and this log is always to the base 2, because here we are going for binary classification. Log base is 2. So basically the probability value, so the log value, because probability value is between 0 and 1, the log value will be negative, and we don't want our entropy values to be negative, so we are adding this negative sign to avoid that, so that the overall entropy value that we get will be positive. Okay, so in this case it will be minus 9 by 14. What is the probability of positive values? 9 out of 14 are positive values, right? So 9 by 14 multiplied by log to the base 2 of 9 by 14 minus, what is the probability of negative class or negative values? Because there are 5 negative rows out of 14, so it's 5 by 14 multiplied by log to the base 2 of 5 by 14. Okay, and if we solve this, the entropy is quite high. You can pause and solve it yourselves. The entropy will come out to be 0.94. The entropy is 0.94. This is the entropy of the entire data set. The number that we calculated over here, 0.94, this is the uncertainty that we have in our data set. This is the impurity. This is the uncertainty that we have in our data set. So information gain will be the entropy of the entire data set before it was split minus the entropy of the data set after A has been used as the splitting attribute. Observe the rows when the outlook is overcast. Here it is yes. Here also it is yes. Here also it is yes. And also here, if the outlook is overcast, the person does go out to play tennis. Okay, so you can say that this is a pure mode. So when outlook is equal to overcast, That means when outlook is equal to overclass, the plate NS, the class label, is always equal to yes. And when the label is same, now we are only considering the subset which is induced by taking the outlook equal to overcast. And in this particular subset, you can see that all the labels are yes. Therefore, you can say that entropy is equal to 0. Okay, this node is pure. There is no uncertainty left. So I can simply say that if the outlook is overcast, then the person does go out to plate NS. Okay, now let's calculate for the other two values. So let's say outlook equal to sunny. Now for outlook equal to sunny, if I label these days, this is day 1, day 2, day 3, day 4, day 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So if you see, on day 1 it was sunny, but the person did not go to play tennis. On day 2 also it was sunny, person did not go out to play tennis. Day 8 it was sunny, but the person did not go out to play tennis. On day 9 it was sunny, but the person did go out to play tennis. On day 11 the weather was sunny, and yet the person did go out to play tennis. Okay, so now we have three instances or 3 days when the person did go out to play tennis when the outlook was sunny, and there are 2 days when the person did not go out to play tennis. Oh, I wrote it. Hold on. So there are 2 days when the outlook was sunny and the person did go out to play tennis, and there are 3 days on which the outlook was sunny and the person did not go to play tennis. Okay, so total number of days when the outlook or the weather or the sky was sunny, total number of days is 5. Okay, so the probability of yes is 2 by 5. Multiply that by the log of probability and append a minus sign because this is going to be a negative number. Similarly, probability of no is 3 by 5. Multiply that with the log of the same, that is log of the same probability, and because this is going to be negative, we use a negative sign. So this is, you can say, the entropy of outlook equal to sunny. This is the entropy of outlook equal to sunny, and this is given as this. Now you can take your time and you can calculate this. So this is 0.971. Okay, so now the only thing left is outlook equal to, so we already covered overcast and we covered sunny, so outlook equal to rainy. 5 rows over here. For overcast there were 4 rows, so total number of rows that we have to consider are 5 for rainy. And let's see, for rainy, on day 4 it was rainy and the person went out to play tennis. Day 5 it was rainy and the person went out to play tennis. Day 6 it was rainy and the person did not go out to play tennis. Day 10 it was rainy and the person did go out to play tennis. And day 14 it was rainy and the person did not go out to play tennis. So if you see the total number of yeses, the total number of rows when the total number of days when the person went out to play tennis despite the rain was 3, and total number of days when the person did not go out to play tennis even though it was not raining are 2. Okay, so the probability of yes is 3 by 5 multiplied by the log of probability and a minus sign. Probability of no multiplied by log of probability and a minus sign, and this will be again the same value, 0.971. So what is the overall entropy of outlook? Now remember these numbers. Entropy when outlook equal to overcast is 0. Entropy when outlook equal to sunny is 0.971, and entropy when outlook equal to rainy. Entropy, this is entropy when outlook equal to rain. So this is equal to 0.971 again. So now we'll calculate a weighted average of these. Okay, so if you see, there were 4 rows out of 14 which were there for the so out of the 14 days, 4 days where the outlook, okay, there were 4 days when the outlook was overcast, so 4 out of 14, and the entropy was 0. There were 5 days when the outlook was sunny and the entropy was 0.971, and there were 5 days when the outlook was rainy and the entropy was again 0.971. Okay, so if we calculate this value, this will be called as the entropy of the entire data set when outlook is used as the splitting attribute, and this value will be 0.694. So basically, if we use outlook as a splitting attribute, we split the data set into 3 parts. One is with the size 4. The size of the first part is 4, the size of the second part is 5, and the size of the third part is also 5. In the partition where we choose the outlook to be overcast, where the partition size is 4, then the entropy is 0. In the partition where we choose outlook equal to sunny as the criteria for creating that partition, so in that case, the entropy will be 0.971. And in the third partition, where we consider outlook equal to rainy as the criteria for that partition, the entropy is 0.971. So effectively, One I have drawn with black over here. These are, so this is like one partition, which is the partition when outlook equal to sunny. The one which I have highlighted or encircled with green, that is another partition when outlook equal to rainy. And now I am highlighting it with overcast. This is the third partition of the data set. Basically, we are partitioning the data set, splitting the data set based on the value of the outlook. And when we do that, when we use outlook to partition our data set, the entropy that we get is 0.694. Okay. So the information gain, it is gain S comma outlook. When outlook is chosen as a splitting attribute, the gain will be, earlier it was 0.94 minus 0.694. So this is 0.246. Okay. Now let's say we repeat everything, and now we choose temperature. So when we choose temperature, now we repeat the entire procedure for temperature as a splitting attribute. So now temperature values, one partition will be based on hot temperatures. One partition will have all those days when the temperature was hot. So temperature was hot on 4 days. Another partition will have those days on which the temperature was mild. And the third partition will have those days when the temperature was cool. Okay. So on the hot temperature days, how many times did the person go out to play tennis? So there are 4 hot temperature days, and on 2 of them, okay, now this is again a no-brainer. So, okay, when the temperature is hot, there are 2 days when the person went out to play tennis, and 2 days when the person did not go out to play tennis. So as I had discussed in the beginning of the video, when it is perfectly half and half, when in a particular data set, 2 of the rows have one label and 2 of the rows, like half of the rows, exact half of the rows have one label, and exact half of the rows have another label, exact half. In that case, the entropy is always 1. So the entropy when temperature equal to hot is equal to 1. This is the highest value the entropy can have. Now let's decide for a temperature equal to mild. So when temperature is mild on the 4th day, the person does go out to play tennis. Here the temperature was mild, but the person did not go out to play tennis, right? Then, so 1 yes, 1 no so far. Then second yes, third yes, fourth yes. Okay, so we have 4 yeses, and when temperature equal to mild, there are 4 yes days and 2 no days. So okay, so entropy will be, probability of yes is 4/6 multiplied by the log of the probability to the base 2 and add a minus sign. Probability of no is 2/6 because there are 6 days, right? 6 days on which the temperature is mild. 6 days on which the temperature is mild. There were 4 days on which the temperature was hot. There are 6 days the temperature was mild. Okay, so the entropy of the partition of the data set where the temperature is mild is given by this. This value comes out to be 0.918. Now the only rows that remain are with temperature equal to cold or cool. There are only 4 days left. So cool, 1 yes. If we count our cool subset, there are 3 days when the person did go out to play tennis and 1 day when the person did not go out. Okay. When temperature equal to cool is minus 3/4 times log 3/4 minus 1/4 times log 1/4. Okay, this value comes out to be 0.81. And now we'll combine these. We'll find the weighted average of this, right? So this is 4 out of 14. This will be multiplied by 6 out of 14. This will be multiplied again by 4 out of 14. Shall I calculate it in this space itself? So it will be easy to refer the values. So this is the entropy of the data set S when temperature is used as the splitting attribute. So 4/14 times 1 plus 6/14 times 0.918 plus 4/14 times 0.811. You can pause and calculate this. So the value will come out to be 0.911. And then what is the information gain now? So gain, when we use temperature as the splitting attribute, 0.94 was the entropy of the entire data set before splitting, minus 0.911. This comes out to be 0.029. Okay. Now the third attribute, that is humidity. Humidity is high. There are only 2 values now. Okay, so it is high on 4. So it is high on 7 days and low on 7 days, right? Consider the subset when humidity. Let's say we split the data set based on the humidity attribute. So let's consider the case when the humidity is normal. Let's say first humidity is normal. So if you actually pause the video and measure, you will find that the humidity is normal and the person goes out to play tennis on 6 days and the person does not go out to play tennis on one of the days. Okay, total number of days where the humidity is normal is 7 days, and of those 7 days he goes out to play tennis. The person goes out to play tennis on 6 days and the person does not go out to play tennis on one of the days. So probability is 6 by 7 multiplied by log 6 by 7. Okay, minus sign, minus 1 by 7 log 1 by 7, and this is the entropy of the partition where humidity is equal to normal. Okay, calculate this value and this comes out to be 0.592. Okay, then let's consider the only other value possible, that is humidity equal to high. This happens on a total of 7 days, and out of those 7 days you can pause the video and verify for yourself. The person does go out to play tennis on 3 of the days and the person does not go to play tennis on 4 of the days. Okay, so the entropy of the partition where humidity equal to high is minus 3 by 4 times log 3 by 4 minus 1 by 4 times log 1 by 4, and you can pause and calculate yourselves and the value will come out to be 0.985. Okay, and now we'll calculate the weighted entropy. So the entropy of the entire data set, if you use humidity as the splitting attribute, this will be equal to, what is the weight of normal? Both of them have equal weight this time. So 7 by 14 is the weight multiplied by 0.592. Okay, that's the entropy of that partition, and the weight of the high humidity partition is also 7 by 14, and the entropy that you get in that partition is 0.985. So this is 0.788. Okay, and what is the information gain? I'll calculate here. So gain in the information when you use humidity as the splitting attribute is 0.94, because the entropy of the data set originally, minus this entropy that we obtained over here, entropy on using humidity as the splitting attribute. So this is 0.152. Now the only attribute that remains is wind. Okay. So windy equal to false, or basically weak wind days. So this is out of these we can pause and verify that. So there are total 8 days, and out of this the person does go out to play tennis on 6 of them, and the person does not go out to play tennis on 2 of those days when the wind was weak. So basically the entropy when windy equal to false is minus 6 by 8 times log 6 by 8 minus 2 by 8 times log 2 by 8. That comes out to be 0.811. Okay, then the only other thing left is windy equal to true, strong wind days. So there are total 6 such days. Okay, and the entropy when windy equal to true, if you measure how many yes values and no values are there. Wow, so there are, this is interesting, when windy equal to true, so there are yes values are 3, no values are 3. So based on the concept that we have studied, the entropy will be 1, because exactly half the rows belong to one label and exactly the remaining half of the rows belong to the second label or have the second label. Okay, so this is 1, and therefore the weighted entropy, the entropy of the data set S when windy is used as the splitting attribute, is the weight of windy equal to false. That weight is given by 8 out of 14, right? On 8 out of 14 days it is windy equal to false, multiplied by the entropy, which is 0.811, plus 6 out of 14 days the entropy is 1. Okay, so this value will be 0.892. Okay, and so the information gain on the entire data set when we use windy as the splitting attribute is 0.94 minus 0.892, which is 0.048. Okay, now if we compare all the information gains, okay, so the gain values that we had, okay, basically, so if I put it like this, the attribute that we used and the gain that we had. So when we started with this, when we used outlook, our gain was 0.246. When we used temperature, our gain was 0.029. When we used humidity, our gain was 0.152, and when we used windy, our gain was 0.048. Okay, so for outlook it was 0.246, temperature it was 0.029, humidity 0.152, and wind windy, it was 0.048. Now, which one of this leads to maximum information gain? And the answer is outlook. So therefore, our first splitting attribute or the root will be outlook. Okay, so outlook will be the root, and there are three outcomes: sunny, overcast, or rainy. Now let's see if we can do some simplifications over here. For outlook equal to overcast, okay, for outlook equal to overcast, we can directly say that plate n is equal to yes. Okay, so in this decision tree we can always do that simplification. When it is overcast, the answer is always yes.